I'll meet with the rest of you after the lecture today. What I want to say is that, well, first off, get started soon. Get started very soon. You should start working on this as soon as possible because there's a lot to do. The second thing is I want to clarify what you need to do about the uses of the analyses. So in addition to doing the analyses, there's two things that I really want you to do with your analyses. One is for the point analysis. I want you to use the results of the pointer analysis to improve the precision of your other analyses. Okay, that's the first thing. The second thing is for the range analysis. I want you guys to use the range analysis to output warnings about out of range, like array out of bounds kind of warnings. So those are two things that I really want you to do and that are required. The other two are optional. If you want to do them, that's great, but you don't have to do them, which is basically the use of constant prop information and CSE information to actually perform constant prop and CSE. So I'm not going to require you to do that, but if you actually have the time to do it and you finished all your stuff and you still want to go the extra mile, you're welcome to absolutely do that. But I'm just not making that part of the project because it's just additional work. And I don't know if you guys will necessarily all have time to do it. Does that make sense? Any questions on that? On the project? Okay. If you go to office hours and you ask a question about the project and you get an answer, then I would like to ask you to go to Piazza and summarize what that answer is. Just kind of put a quick summary for other people's benefits, okay? Because basically you're getting an answer. I just want to make sure everybody gets to see those things. The second thing is feel free to post on Piazza. The kid's going to be looking at that and answering questions about LVM. But feel free to post so that other people can see your questions. And other people, if you see questions, feel free to answer. It's okay to share small snippets of code after maybe 3 lines or 4 lines of code. If someone asks, well, how do I get this gizmo from this gizmo? Or how do I set the gizmo on that thing? Or how do I do this? Maybe you can actually, share several lines of code, but not more than that. If you want to share more than that, then you should be careful, because we don't want to be careful about it. The other thing is, if you feel like you need other people's support, you guys are welcome to work all work at the same time, either online or in the labs, and you can ask each other questions. You can ask what other people are doing. If they have advice, if you're confused on something, you can ask other people. But don't share code amongst different groups, right? You can share code amongst a group, but across groups, don't share code. Does that make sense? So the idea is that, think about it this way. Everybody in the class is doing the same project. So the people next to you are doing the exact same things. They're facing probably similar problems. So if you actually have, I want you guys to kind of leverage each other's kind of, ability to figure stuff out. So you guys you're not on your own. Does that make sense? Okay. Okay. So let's continue where we left off. So, do you guys remember where we left off?
At the end.
We left off at the end? We left off at the end of last lecture, and we left off at the beginning of today's lecture. Yes. That is a correct assessment. So what have we just seen? What did we see so far in point analysis? We saw intra-procedural point analysis.
Collapsing.
We saw a whole bunch of collapsing. So what did we see for collapsing? So we saw, what do we see? So we saw that we started off with point analysis where we compute pieces of information at every edge, and then we said if we want to do that for the entire program, that's a little bit crazy, so what we're going to do is instead we're going to collapse all the information for all the edges into one control flow graph. That's right, one point to graph for the entire program, or the entire procedure we're doing, and we're going to basically just do it in a flow-insensitive way, right? That was the idea that it doesn't matter what order you process statements in. If the order doesn't matter, you're just going to compute one piece of information for the entire program, but you lose precision. But we saw that even that you need to iterate, so there was another algorithm, so that was called Anderson. We saw that even that's very expensive, and there's another algorithm called Steensgaard, which is almost linear. And what that does is that it adds the additional constraint that every node in the pointer graph needs to point to only one thing. Okay? So you only can point to one thing, and if you point to two different things, then you have to merge those two things into a summary node. Okay? So let's take a look at another example. This is another example of Steensgaard. So this is how this will work. So, so one way to do this is that when you see these kinds of, this is pretty, So what is this going to do? So this is going to do I points to A, right? J points to B, right? Now, how do we model this function call? So what we're going to do is consider that P is a global, and this is going to be basically like assigning address of I into P, right? So P can now point to I, right? Good so far? So and now what do we do? Now we handle this statement. So P points to J. If this were Anderson, this is it would be done, but this is not Anderson, this is Steensgaard, so what do we do with Steensgaard?
Collapse I and J.
We have to collapse things, so really what we're going to get is these are going to become one node, and because these are one node and they point to two different things, this is going to become one node, so what we get is something like this. Right? So, now, notice what happened here, which is really, really weird, right? So now you actually ask, what does I point to here? So according to the Steensgaard analysis, well, first of all, if we did Anderson, this is what we would get. Okay, we would keep these separate. So if we ask Anderson, what does I point to? What is it going to say? It points to A, right? If we ask Steensgaard, Mr. Steensgaard, what does I point to? What is it going to say?
A, B.
A, B. That's a weird, so that's a very interesting thing that this I here now basically can point to either A or B. And you see why this happened, right? The reason why it happened is because address of I and address of J were passed into the same parameter, P, and that caused this pinching point, right? This P is kind of this pinching point where basically you get this this kind of collapse. And there's actually some research that was done to actually kind of avoid. So this kind of collapse is very common to see because it's very common to have pointers as parameters to functions, and so it's very common for basically these parameters to functions to be basically these kind of pinch points that point to many things, and they collapse everything that you pass in. And so there's actually been some research where it's called one-level flow, where basically you only keep basically one level of flow, and then beyond that you kind of collapse things. So if this points to two different things, you keep these separate. But then later on, beyond that, if you get multiple things, then you actually then you collapse them. Yeah.
So like, if there was a nested call inside of the one-level flow, would handle that?
Well, it's not necessarily a nested call. It's more, what would the nested call do? It's more that if this A or this I pointed to multiple things, it would collapse those. So it's not really about the nesting of calls necessarily, but about what I could point to. So if I point to multiple things or A pointed to multiple things, those those would get collapsed. But the point is that there's many ways to do it. One is to basically say every parameter to a function, you allow it to branch to multiple places. That's one way to do it. And then everything else collapses except for the branching of the parameters to functions. That's probably the easiest way to describe it. Okay, but notice, you guys see what happened? It's kind of like very sneaky, right? It's that basically this I and J got merged because they both got passed into this P, whereas Anderson didn't merge them. Now, okay. Fine. So that's the linear time thing. That's fine. I mean, there's an inverse Ackermann function in there, and you guys can the point is that you're using basically a line data structure to actually implement this kind of, when you actually implement this kind of thing, you actually, when you merge these things, you basically kind of, you store these unions, and basically when you want to find a representative for a particular variable, you kind of, you find the representative set for a given variable, and that gives you the set. So, and it turns out that it's actually pretty efficient to implement this. Okay, so this was the example from before, which we did using Steensgaard. We used Anderson last time. So now, what you guys are going to do, Steensgaard. Remember we did Anderson with this, and we came up with this kind of really convoluted kind of, graph about how it works. So now, Steensgaard, so remember the way it works is you do like Anderson, but when you get to a node having multiple outgoing edges, so node, multiple outgoing edges, you collapse the outgoing edges into one. So you guys can just try that out and see what happens. Okay. So I started off the analysis here. So P points S1, P points S2. That's the same as before. Nothing's changed there. Okay, star P gets Q. So this is so star P is S1, and then Q points to S2. So star P gets Q. That will make. What are you going to do?
S1 to S2.
Like that, right?
Yep.
Okay, now we get R gets Q, so R points to Q. And notice that what's cool about this is that before we had to iterate, right? We had to go through these and kind of figure out a bit, but with Steensgaard we don't have to iterate, okay? Because everything points to at most one thing. We had to iterate before when we had something pointing to one thing, and then later on it would point to multiple things, which would kind of cause us to have to go back and redo pointer assignments. But now we don't have to do that because it points to at most one thing. So R points to Q. Now what? Star Q. Okay, star Q. Which one should we do? Star Q gets what? Which one? This one? Okay. So star Q gets P. So star Q is S2.
S1.
S2 points to S1?
Mm-hmm.
Okay. Okay. Now which one do we do? Which one? It doesn't matter the order. Which one should we do?
S and
Huh?
S is P.
Which one?
S equals P.
S equals P. Okay. So S, we'll just do that, right? Okay. Now what?
Star Q is
So
R.
this one, star Q gets R?
Yes.
Okay. So star Q is S2.
Mm-hmm. And it's R.
And S2 will now point to Q, right? Because R points to Q, right?
Right.
Okay.
Problem.
Uh-oh. Okay. So what happened? So S2 now points to multiple things, so we need to collapse some stuff. So what do we collapse? Oh boy, this is gonna be
Q
bad.
and S1.
Wait, S1, okay, so I'm gonna collapse S1 and Q. Oh boy. How am I gonna do this?
It's like a diagonal.
Oh yeah, it's like a diagonal, is that what you're saying?
Yeah.
Wait,
Now it points, now
so
the,
S1 now just points to this one supernode,
yeah. And
and now this supernode points back to S1, right?
S,
That's S2.
S2, yeah,
Okay, that's it,
yeah.
right? Cool.
Now S is R.
Wait, which one did we do?
Star Q is R.
Okay, now we got this one.
S is R. So it's nothing, already did it. It's already pointing
Wait,
it.
S equal R, oh yeah, because R already points to the blob. So see, I mean, I guess, yeah, this would have, we basically already merged Q and S1, so, okay, so what next?
Star R is S.
Wait, star R.
So now it has to point to S.
Okay, hold on.
Oh, point to
So
itself.
star R is this thing, and it needs to point to itself.
Yeah.
Okay, so now this blob has two outgoing edges, one to itself and one to S2. So we need to then suck in S2. So basically what this means is that whatever the target of these two arrows needs to be merged, in other words, the blob needs to be merged with S2. So S2 will then go into here, and the self edge will still remain because S2 points to this blob, so that's going to remain the same, and then we get this, right?
Yeah.
Right? Okay. So that's what we get with Steensgaard, and notice, so this is what Steensgaard gave us, right? And this is what Anderson gave us. So you notice how Anderson basically was able to keep everything separate. We get much more detailed information about the pointer relations. In Steensgaard, actually, in some sense, it's much simpler, right? The structure is much simpler, but you lose a whole bunch of information. For example, what's an example of information we lost?
Anything in the super block?
What?
Anything within the super block?
Right. So, for example,
Or rather,
in this thing, we know that actually, what is the information we lost?
like you lose the fact that
No, but in this
things
example-
aren't pointing to each other.
What?
Like
Oh yeah. So S2 doesn't point to itself, whereas there you lost that. Is that the only one? That's probably the only thing, isn't it?
S doesn't point to S2.
Oh, S2 doesn't point to Q.
Mm.
Oh no, it does. It does.
It's the other three now all point to the super block, where before they only point to one or two things. Like
Oh right. So before P did not point to Q.
Or S2.
Or S2. But now totally lost that, right? You totally lost that. So yeah, so there's a lot of, and S didn't point to S1, to S2, so there's a lot of information you lost by merging all those things. Yeah.
Why don't you merge S1 and S2 first, according to the Anderson analysis?
Wait, in Anderson? In
Yeah.
Anderson, we don't need to merge.
Yeah, I mean, but from the Anderson analysis.
Oh, you could merge, so,
Yeah,
yeah.
you can merge S1 and S2.
Yeah, you
first.
could, sure. Well, what you mean in Anderson? So in Anderson, I'm confused. So first of all, we chose to keep S1 and S2 separate, but we could choose to clobber them together even in Anderson by just saying, you know, we're going to have one heap summary. Here we have separate heap summaries for what was constructed at S1 and at S2, but you could basically say, I'll keep one summary of the entire heap, a heap summary. And then S1 and S2 would be combined together into a heap summary, summarizing the entire heap. But you choose to do that. Anderson doesn't force you to do that, right? So in Anderson, you're allowed to keep these things separate. In Steensgaard, by the way the analysis works, it forces you to merge them. Does that make sense? Or I mean, I guess you
No. You do the Steensgaard analysis, but based on what you have done the analysis before, which is mostly similar to Anderson, right? And you choose to first merge Q
No, we just picked a random order to run these things. You could run it in any other order, you would get the same answer.
Yeah. I mean, so we can we can choose to merge S1 and S2 first, and then merge Q to the.
Well, I don't know if you could. I mean, you don't choose. You only choose to. Sure. I mean, there's probably an ordering that forces you to merge S1 and S2 first, but you only merge things when you have. I mean, it's not like you choose to merge S1 and S2. You just merge things when you have multiple.
Yeah, but if you go the other side, not the right side, but if you go the left side, you will get you can merge S1.
Yeah, and you would get the same answer.
Because you will have multiple errors.
Right. Absolutely, but you would get the same answer.
Yeah.
Right. So absolutely, the order in which you process statements will cause the merging to occur in different orders, but at the end you'll get the same answer.
Same answer, and you have to go over every instruction anyways, right?
Yeah.
So order shouldn't matter at all.
Yeah, order does not matter, and the point is you only have to go through every instruction once. And actually, if you just ponder, I mean, this is really cool. I mean, it's a very, very deep. It's because everything we've been doing so far is all about iteration. You always have to iterate. Even in Anderson, you have to iterate. But here, it's like just one shot, linear through the program, and you're done. Right? So it's kind of a very different way of doing. Yeah.
Any intuition why you should always reach a single solution?
Yeah, that's a good question. It's hard to explain. I mean, I guess the point is,
You never.
yeah, that's hard. I don't have a good intuition.
Well, one way to say it is you're never losing anything that a prior statement said, so redoing it won't help you. Like the blob stuff, you lose negative.
Right, but what he's saying is not. What he's saying is why is it that different orderings of statements will get you the same answer? I mean,
Each statement can or cannot provide information, though, and you're never going to lose that information once.
yeah, I know, but it's still kind of weird because basically you can actually have different. I mean, the fact that you actually arrive at the same answer, but through completely different merging operations, it's kind of an interesting thing, right? I mean, you can get to the same final answer, but the merges are the intermediate states are completely different, right? So, I
guess it's kind of like a proof by contradiction. If you say, how could it possibly matter on the order?
right.
And then you'll find out that, well, I'd be doing the same thing no matter what. Like,
Right, no, I know, but I mean, but another way to think about it is if you were to prove this, I mean, I don't know how I'd actually prove it, right? If to actually really brought a really kind of foolproof argument that actually you do get for sure the same answer. Yeah, do you have an idea?
Like, imagine the internal state of the algorithm as like a graph with edges from one state to the other of that graph, and then prove that there is a unique like terminal node by contradiction. So even if you find a directed path through this graph that doesn't matter sort of which way you go, you non-deterministically find.
Right. I mean, and sometimes what you can show is that there's a unique. What you want to show is there's a unique. Given that you have this constraint that every node points only one thing, which is actually it's almost like every node has a single type, and the type shows what it points to. That there's a unique answer for the program. There's only a unique set of ways of solving those constraints. That's really what it is. But yeah, we can. Yeah, I mean and I think you have to work out the theory to try to show this. So I don't know. Does that intuition help you? A little bit. Trust me.
There should be some research on this.
What?
I think there should be some research on this.
Well, I mean, I think if you look at the original paper on this, the Steensgaard paper, it's actually quite theoretical, and I think there's a lot of interesting stuff there. And so, most likely people have, I'm sure that people have looked at this. So actually, if you go to Google or you go to the original paper, they might actually even show that there's only one set of, there's only one type inference. There's only one set of types that can actually possibly solve it. Yeah.
Basically, each instruction that causes a merge of some sort will always cause a merge. The element might already be merged or not, but the same instruction will cause a merge.
No, I don't think so, actually. That's the problem. I don't think so, because it depends on the order. So, for example, if the first instruction that you execute so let's say that when we did our thing, we had this instruction which caused a merge. If you run this instruction first, that's the first instruction you process, which you can do, and that's not going to cause a merge, right?
Of course not.
Right? I mean, because it's literally, if you start with this, what will happen is you'll get a Q. Basically, what you'll get is you'll get a Q, and then you'll say, well, Q must point to some blob, which I'll call star Q, and then P, so this P must point to some other blob, and then you'll get this, right? Star Q is P, right? So you'll create the things that P and Q point to, because eventually you know that there'll only be one thing. So you can kind of create the node there, and eventually whatever, if Q points something else, that'll get merged there. So, yeah.
Yeah, but I think sometime last class you mentioned, if we assume that every variable is already pointing to an empty block, then like every statement is going to create like some sort of branch with an empty block.
Sure, you could do it that way.
But then like what Andrea said would probably hold.
Yeah, but it's still the case that, yeah, I mean, that is true. So if you do it that way, maybe that's true. It still doesn't quite elucidate entirely for me what, like, the fact, yeah, it's not an entirely convincing proof that you actually will get the same answer. Well, you guys can look, so, I mean, the thing is this. You guys can look it up online. I'm sure that people have looked at this. You can say Steensgaard unique answer. And Google will help you. Okay, so let me skip this. I mean, I'll skip this because we're going to read papers next week about point analysis. So we will talk about that then, about the more advanced stuff. How do I exit out of here? All right. So that concludes pointer analysis. We only have two more modules in the course: program representations and interprocedural analysis. So we're getting to the end. We're getting close to the end. So let's talk about a little bit about program representations. So far, a lot of what we've done is with CFGs, and what we'll do is we'll kind of talk more broadly about what kind of representations you want to use to put your program in. Wait, what happened? Uh-oh. Wait, my pen's not working. Oh, man. Wait, it's really not working. Huh. Oh, well. Okay, we'll do without a pen for a little bit. We'll survive. Okay. So what are the goals for representing your program? So, you know, you want analysis to be easy and effective. You want to be able to write your flow functions in a relatively easy way. You want to enable transformations to be easy. And we'll see that different representations actually encode transformations differently. And you want your representation to be general enough that it can encode many different input languages, because the idea is that you'll have your compiler should be able to parse in multiple languages, not just one language, into an intermediate representation. Now that's kind of the primary thing. Of course, you also want it to be relatively compact in memory. You want it to be easy to translate to and from, right? Because actually when you create one of these representations, it's actually, you have to translate to that representation, and then after that, you have to translate back to assembly code or some kind of low-level thing. And we'll see that this is actually key. There are some representations that are very, very hard to translate to or from, and that's actually really impacted their ability to be used in practice. Representations, you'd like them to be able to track things like debug information, so that then when you generate the code or generate your assembly, you can actually have a relation between what's happening there at the low level and the original C source code, or original source code. Extensible, displayable is actually a big deal, or understandable. So as we'll see, I mean, there's some representations are easier to understand than others, and that actually really, really impacts how much they have an impact in practice. So there's many. This is a huge research area. We've been looking at representations forever. There's so many different things. We'll only cover the tip of the iceberg. But let me just first say, I mean, one thing you could do is you can really go super high level, right? So this is a piece of code, and this is the AST. So this is very, very high level. This is abstract syntax tree. It's just the syntax, the syntax tree, the parse tree, essentially, of the program. Now, this is very high level, very close to the source language, and what? Is it good or is it bad?
Bad.
Bad. Okay. Okay, why is it bad?
Do analysis.
What?
It's hard to do analysis.
Yeah, so, well, okay, so it's hard to do analysis the way we set it up. We want a control flow graph, we want something where we analyze. It's hard to do vehicle analysis on this kind of stuff. Now, of course, people have come up with all kinds of analysis frameworks for these kinds of things. There's these things called attribute grammars. Do people know what attribute grammars are? Does anybody know? So an attribute grammar is like a grammar, but it allows you to store information at the nodes of your parse tree. So it turns out that there's actually ways of using these attribute grammars to compute information across these nodes, and so that's kind of a whole other analysis technique that's kind of very niche. It's a very small community who do that, but one is that people have looked at this. We actually write not a very, you know, if you want to do analysis of this kind of stuff, it's not the most standard thing, especially like you see, you want to see if you have multiple statements, you want to see where the control flow is, it might be a little bit hard. Now, okay. But what? What's good about this? Obviously, this is not all bad. There must be something good about this. What? Easy to display, easy to understand, and what else? From the point of view of an analysis engine, if I wanted to do analysis on this. Yeah.
It contains a lot of information. Has everything.
It has it has everything that was in the source code. It has all the for loops that are in the source code. It has all of the array instructions from the source code, so I can see all the array instructions. In a lot of what we've been doing with our stuff, it's all just pointers, and it's all just the loops are all the control flow graphs. So we actually have to, in some cases, if we want to figure out where the loops are, we have to do some kind of traversal of the control flow graph, and you find these back edges, and the back edges represent loops, et cetera, et cetera. Right here, you have all the loops. You can see the array instructions, so you actually do have some information that actually is useful. So it's not totally, it's actually a trade-off in many ways. So if you have, this is a low-level IR, this is very similar to what, you know, LBM is, or what we've been looking at, where you have basically kind of these really low-level instructions, and they're basically put together inside of the control flow graph, and so if you see this as a source, this is a low-level IR, so what's the benefit of this? Well, the benefit of this is we have a control graph, we do data flow analysis, but what more? Well, so notify loop, you don't see the loop structure anymore, you don't see the array axes anymore, right? It's much more complicated to see where you're accessing arrays, etc. But why would you, what's the benefit of this kind of low-level thing? So notice this in here, right? It's I times 4. And notice it's I times 4.
Mm-hmm.
What's that? Huh? That's a what?
I'm assuming that's like some kind of memory alignment.
Well, yeah, I mean, it's basically, it's some kind of memory, yeah, I mean, it's basically computing the kind of the indices. It's actually because this is an array of elements of 4, of size 4. Right.
Mm-hmm.
But these are two expressions, and they're the same expression, right? So this is a common sub-expression elimination. So the point is you can actually do optimization at this low level that you wouldn't even be able to see at this level. These things don't even exist at this level, right? So once you actually lower it and look at this at a very low level, you can actually see optimization opportunities that you basically weren't even visible at the higher level. Now the reality is that is that in some sense, basically you mix multiple representations in the same compiler. You start with a high-level representation, do some stuff there, then you lower it into kind of a more general intermediate representation where you do some stuff, and then you lower even lower level where you get very close to the assembly, and you can do things like branch trial allocation. You can do what are called people optimizations, where you kind of do little small rewrites that make things go faster. So, okay, any questions on this? Okay, there are two components of an intermediate representation. There's the control dependencies and the data dependencies. The control dependencies represent the kind of the ordering of the instructions. So things like evaluation of ifs and else, you know, things like exceptions, the control of the program, right? Which instructions get executed. The data dependencies basically represent the flow of values from definitions, from the places where the values are created, to the uses of those values. Okay? And the ideal here is that you want to represent just the dependencies that matter, right? In the sense that you want to represent the smallest number of dependencies that really makes your program, defines the computation. Okay. So as an example, let me give you a very simple example. Oh no, I can't write. I can't give you an example.
Board.
Okay, what?
Board.
Oh man, I'll give you an example without the board. This is you're gonna have to imagine it.
Okay.
The example has two instructions. Oh gosh. It's really simple. The first one is x equals 5. The second one is y equals 6. Two instructions. And you put them in a control flow graph. So you put the first one, the x assignment, and then y assignment, right? And you have an edge between them. Now, that control flow graph represents the control dependencies between these two instructions, but it represents those control dependencies in a way that that is over-represented, because in that program, you don't actually need to execute those instructions in that order. You can execute them in the other order around, right? You can execute the y instruction first and then the x instruction. But the control flow graph can't represent that. The control flow graph forces you to pick one order or the other. It has no way of representing the fact that in some sense those two instructions really don't have to depend on each other in terms of a control and the control flow graph, in that sense, is very, very constraining. It really forces you to pick the order of instruction when, in fact, many of the instructions in the program are not ordered. So that's why it's actually the control flow graph is one of the simplest representations, but it's also extremely constraining. Okay. How do I get my thing to restart? There should be like a restart button.
Can you turn it off and back on?
What?
Can you turn it off and back on?
The computer? Yeah, I can't do that. Let me actually, you know what? Let me do a small version of this. I'll just put it to sleep. And then I'll turn it back on. Let's see if it's going to help. Do you think it's going to help? No? Oh, wait. It's working again. I didn't even need to put it to sleep. Wait, hold on. Let's see. Yeah. It's working. Okay.
Oh.
Wow, that's cool. Okay. So this is okay. So now I can, but now we've done the example, but it's okay. It's okay. It's gonna be fine because we're gonna have many other examples. So did everybody understand that example? Two assignments. The point is, control flow graph constrains you. It constrains you. You have to pick an ordering of those instructions. You can't leave them unordered. Okay. So let's talk a little bit about control dependencies. Actually, very, very briefly, basically you can do a control flow graph. That's kind of the standard way to do it. You can do control flow graph with basic blocks. That's what you have in LLVM. Control flow graphs are really the main way to represent control dependencies. There are more advanced options, like the control dependence graph and the program dependence graph, and we're going to see those later. They're very interesting, weird, advanced structures that nobody uses, but they're really interesting to understand because they're really, really cool. But their use in practice has been impeded by a variety of things, and we'll talk about that. So more on these more advanced things later. But what I want to switch over to is data dependencies, okay? So the simplest way to represent data dependencies is what's called depth use chains. Did we talk about depth use chains yet? We haven't talked about them, right? What's a depth use chain? What do you think a depth use chain is?
Definition.
Definition and uses, and it chains the two together. Whoa. So, for example, in this example here, so we have our so this y, for example, this is a use, and it will basically maybe link up to that definition. And then this is a use, and we will link it up to that definition. And right? Does that make sense? And then this x goes to here, and then where does this y go to? Oh boy.
So y is times.
Etc. Right? You can imagine. So putting, this one goes to this y and that y, etc. So how do you build a depth use chain? You use this kind of depth use graph. What analysis would you use to build this? Huh? What?
The liveness analysis, something like that.
You can use liveness, but actually, I think you want more than liveness. Because what you want is you want to know not just whether a variable is live, but you want to know where did it come from. You guys remember this? Reaching definitions. This is like, it's such a long time ago. I mean, this is the first thing we did was reaching definitions. So if you compute reaching definitions, then for every definition you know where it came from, and you just create a graph that's overlaid on top of, well, you create a graph that links every use to its definition. Yes?
We don't take care about y comes from x plus y.
Say again?
We don't care if y comes from x plus y. We just care about any point of y.
Yeah, well, what we care about is we link this use, the fact that y is used here, we link it to wherever the definition. Right? Basically, it's a way of, when you have a use of a variable, it's just a way of linking it to all the places where that value could have come from.
Okay, and that's like this going from what that variable may actually be. Right?
What do you mean by that?
Like, it doesn't really put any information about the actual value.
No, well, it doesn't, but it allows you to track information about the value. So, for example, I can go and look at this reaching definition. I can see if at this y, all the reaching definitions are assignments of the form y equals 5, then I can replace it with 5. Right? And I can do that without using any data flow analysis, nothing. I just look at the depth use change, I look at this y, and I'm like, oh, this y, oh, that's y equals 5. Oh, that's y equals 5. Therefore, that should just be 5, right? So it's a different way of... Now, okay, so let's suppose, okay, now this is very exciting. We have these depth use chains. I'm very excited about this. We have a new graph. So far, everything we've been doing is with this control flow graph. Now we have a new graph that links these variables to the original statements that use them. Now, in my excitement about this new representation, I would like us to now throw away the control flow graph. Because now we have a new representation, right? So can we throw away the control flow graph?
Probably not.
Okay, we can. Sure, okay, you can do it. Let's throw away the control flow, and what happens? What?
You lose all the information.
Well, it's not just that you lose, wait, so hold on. Let us just be very careful here. Sometimes losing information is fine. For example, when we went from Anderson to Steensgaard, we lost some information out of the pointers. That wasn't a big deal. There's some kind of information that when you lose, it's not good because there's a particular, the original program has some semantics. If we throw away too much stuff and we can't reconstruct what the original program was supposed to do, then that's a problem, right? And so if we throw away the control flow graph, we actually would not be able to reconstruct the actual, the program execution of what the program is supposed to do because we're losing branches. We don't know where the values of branches came from and the ordering of statements. So we can see that this y came from here and from here, but we don't know what the order of these things were or which branches they were in, okay? So this kind of depth use chain, which is also sometimes called a data flow graph, okay? So it's a data flow graph that tells you where the variables come from in terms of their values. These kinds of things actually are not complete. So you need a control flow graph underneath to actually tell you what the ordering of instructions are. Okay? So the data flow graph is something you superimpose on top of the control flow graph. Now, one of the cool things about this kind of data flow graph is that you can actually do data flow analysis on this data flow graph. So instead of doing data flow analysis on your control flow graph and propagating information on your control flow graph, so for example, in constant prop, you propagate information on the control flow graph, and every one of these edges has a map from variables to values, right? Variables to all the constant values that we have. Well, another way to do it is instead of propagating across these edges, you can propagate it across the data flow graph edges. And in that case, all you need to propagate is one value. So for example, here I can propagate this, if this y is 5, because it's assigned 5, I can propagate this 5 to go all the way down here. And I can then propagate it to all the uses. Instead of having to propagate the y maps to 5, right, the y arrow 5, through every single statement all the way down here, in this way there's almost like a little slide that allows this 5 to go all the way down here. Right?
Hmm.
Does that make sense?
Mm-hmm.
Okay. Now,
are there special, like we have two branches here. If we imagine that they're actually branching on the same thing,
yes.
then what would it be called? Like we're saying, oh, is there a special way to like prune your deputy chain? Like with the two Y's on the left.
Right, there are ways, I mean, there are very sophisticated ways of doing data flow graphs. There are even ways of making data flow graphs executable, so you actually give them information about all the branch information and all that stuff. So there are ways of, and then you get very close to kind of these data flow machines and data flow languages that allow you to, so there are ways of kind of extending those to be much more complex. But for now we're considering just a basic thing. Now, one thing you will notice that this representation is quite expensive in the sense that this y will go to these two places. Every possible y in the program will go to every possible definition, right? Because any definition up here, well, at least in this example, right, all these y's will go to both of these definitions. And we'll see that there are ways of actually reducing that overhead. Okay. So it's relatively space consuming. So now we're basically going to do, we're going to introduce a new idea which you guys already know about because you guys have been doing LLVM, but from the point of view of the in-class material, this is a new idea which is a twist on the data flow graph. So the idea is that it's a static single assignment. So this is an idea that has been very, very successful. Widely successful. We'll see why it's been so successful. So the idea of static single assignment is that you will only allow one, every variable can only be assigned once in the program. There's only one assignment per variable. Now here, this thing is not an SSA form. There's no, right, because here you have one assignment and here you have another assignment. Both of these assignments to the same variable. So this program does not satisfy the SSA constraint. So how do we make this program? So this is a state program. How do we make this program satisfy our SSA invariant? You guys know? Rename. So we're just going to rename things. So every time we see a variable, we're going to rename it. So here, for example, we're actually going to subscript things. So we're just going to say this is x1. What about this? This is y1. This is going to be x2. This is going to be x3. This is going to be y2. And this is going to be, I don't know. There's no more assignments. Those are the only assignments, right? So I rename, every time I have an assignment, I have to create a fresh variable. So I'm going to rename all the variables to create that those two assignments to x are different variables and the two assignments to y are different variables. Actually, there's 3 assignments to that. Okay, now what? So now you just basically look at the uses and you basically do the right thing. So this is going to be x1, this is going to be y1, this is going to be y3. Oh no. Y1, and this is going to be x3, and this is going to be x2. Ha! And now what do we do with this y? This is going to be what? y1 or y2?
Y2.
y2?
Oh.
Oh,
Oh boy.
Either Y1 or Y2.
So no, sometimes we got to create y3. So well, okay. So wait. So it's going to be either y1 or y2.
Right. If you assign Y to
Huh?
some temporary variable that is one or the other.
Right. So what we can do is we can basically say, you know what? We're going to create a new variable, call it y3. And we are going to say that it's going to be either y1 or y2. You guys know what the node is here? What this node is? So it's actually an operator called a phi node, which basically says it's either going to be y1 or y2. This phi node is an oracle. It's a special thing that will just tell you, magically give you the right value. Okay? Cool. And now what do we do?
No, that's Y3.
Now we do x3. Oh yeah, this is all y3. And we should do that for x3 as well, right? Just for the sake
X4.
of, well, that's fine.
We already have what, X?
We already have an x3, but we have multiple x's. We have x2 and x3 here. So for the use of x down here, then we should do x4 is equal to phi of x2 x3. Right? Right? Okay. So now we have the concept of the phi node. The phi node basically is a magical mystery box that gives you the right thing. It just magically gives you the right thing.
I have a question. So I'm thinking of like, what if there's a loop where you're incrementing, you know, I a million times, and so are you going to have a million?
Times,
Yeah. Are you going to have like a million different I variables and then a million different things in this phi?
Sure. So if we have I equals 0, and then you're basically saying, then we have the loop, where we have I equals I plus 1. And then this loops onto itself based on some condition, let's say I is less than 100 or something, or less than a bazillion. Okay, how do we do this in SSA form? How many assignments are there here? There's 1 assignment and 2 assignments. Right? But now what happens is, what do we do here? We have the same problem, right? Because this I comes from here, and it comes from here. Right? So we need a way of merging the I2 and the I1, and the way that we do it is that we merge these two into a phi node up here, into an I3. Right? So basically, this I1 equals 0. This phi node chooses between either this value here or the value that came from the bottom, and this now is I3. Okay? So that's how you have loops. Okay, does that make sense? So that's the way you, so we create a new variable for each definition. So we go through the program. Every single assignment that we see, we rename the variable. So every assignment to the same variable, you have to rename it to make sure that every assignment has only one variable. And then, once we do this, we have to insert the phi nodes at merge points. So merge points are where you essentially have to insert phi nodes, because at merge points, you have multiple different, let's say for I, you might have I coming from one branch and another I coming from the other branch, and you insert phi nodes there. And then you have to adjust the uses, all the uses throughout the program to refer to the most recent version of the variable. Now, how do we insert phi nodes? Well, it turns out that phi node insertion is a very complicated topic. People have done a lot of research on this. It turns out that there's many algorithms for doing this. Some are there's optimal space print. There are many ways to do this. But the simplest way, what's the simple way to do it? Well, let's suppose you have a liveness analysis and a Ricci definitions analysis. How would you do it? Well, what you could do is, if you find a merge point, let's say there's only two, so let's say you have a merge point, and there's a variable called x, which is live here, and it has multiple reaching definitions, right? It's live, and it has multiple reaching definitions, then you probably need to insert a phi node for that x here. Because it means that you're at a point where you can come from two different places, and there's reaching definitions along both sides. Okay? The point, though, is that there's many algorithms for doing this. This is kind of an intuition of how you do it, but we're not going to go more in detail on that. I guess what I'm trying to say here is that it's relatively, even if there's many, many ways of doing it, it's relatively easy to figure out how you would do your own version of this. Like, you don't have to, like, follow some complex algorithm. All you need to do is liveness analysis, reaching definitions. You look at the live variable at a merge point. If there's more than one reaching definition, then you insert a phi node there. Okay, so that's how you convert to SSA. Now, what about, now, fine, again, you can create this SSA, but at the end of the day, there's no assembly instruction that runs like the phi node. So you have to somehow get rid of them before you can run your program. So how do we get rid of phi nodes? Yeah.
You go to each origin basic block and define x3 equals x1, and the other block equals x2, and depending on the path it comes here and then forward.
So, okay, let's be more concrete. So we have a node here, x3, is equal to phi of x1, x2. Okay, now what do we do?
So now I will go to the previous basic block and define x3 equals x1 on the left state and x2 equals x2 on the right.
Yeah. This is, yeah, so basically you go to the last basic block on this side, and then you insert this assignment, and then on this side you insert this assignment. Right? And notice how simple this is, right? It's really, really easy. All you're doing is you're inserting assignments to x3, and it just deals perfectly with doing the right thing. It's going to set x3 if you come from this side, so you insert these assignments at the end of the basic block that came in from these two areas, right?
I think you used to reverse x1 and x2 were assigned. Because we don't actually know that it was from those basic blocks, right? Like it could have been farther up the control flow graph.
Yeah, but that's harder to figure out because, I mean, this is definitely correct, right? Because you're coming, I mean,
if we know that x1 was assigned on that left block and x2 was assigned on the right block, then yes. But what if it was a higher block up, for example?
Well, no, I mean, so this is the assumption when you have these phi nodes is that the first, the phi node is basically has one entry for each.
Oh, it's just those arrows that it is.
Yeah, I mean, basically there's three input edges here, there should be three parameters here. Right, so basically this phi represents, this is the x, you take either the value of x1 that came through here, or the value of x2 that came through here.
So we're not putting this x3 thing where we first read x and realize that it's a mix-up. We do it when we have a merge, and there's a...
Wait, the phi node you mean, or?
Right.
Yeah, the phi node is always at a merge.
Okay.
The phi node is always at a merge. The point is to put it at a merge point where you have an x1 coming from one side and an x2 coming from the other, and it's like, what do? You merge them into the x3. Yeah, so this is definitely the simple, and it's very local, right? I mean, all you need to do is just insert, you just do immediately after, you know, previously, and then that's it. You just insert that instruction. Now, what's cool about, so this is super simple. Look how simple this is. Really, really dirt simple. Really, really cool. Now, the other thing that's important to keep in focus, does this make sense? The other thing that's actually really interesting is that basically when you look at the way it's done, and then you delete this thing, right? So you then delete this phi node, and later on here you'll have an x3. Now, if you remember when we talked about register allocation, we talked about how register allocators are smart, and what they do is they compute liveness information about your variables, and they they reuse registers based on the alignment information. And so it turns out that because this X, depending on how you do things, but if you just take a program, convert it to FSA, and then convert it back, X1 will not be used later on here. Later on, you'll only have X3 being used, right? Because X3 was here, and then everything else will be X3. So basically, X3 will be used here. X3 begins to be live here and will remain live here. And X1, this will be the last use of X1 because previously you had X1, but now you're done with X1. So basically, what will happen is the register allocator, in many cases, unless you do optimizations, will actually be able to allocate one register to all of these different X's. So what that means is that you'll be able, because these different X's, these X1s, X2s, X3 will have non-overlapping lifetime ranges, you'll be able to assign them to one register. So it's not like you're actually, by adding these different variable names, you're not necessarily increasing register pressure. Yes?
Well, that's assigned variables, so that makes sense, right?
Well, it makes sense, but, as we'll see later on, when you start moving things around, stuff gets interesting. Because, for example, this, in the original program, everything down here was X3. But once you optimize things, you may be able to, use X1 here. For example, if it turns out that X1 has some expression that you really care about later on, you may actually now have uses of X1 later on. So now X1 will overlap with X3 in terms of alignment. But that only happens if you actually transform the program. If you don't transform it, you just keep it the original way, it will actually be able to allocate the same register. Because it is indeed the same variable. You're absolutely right. Yeah.
Having those X3 equal to X1 and X3 equal to X2, it did not really change the original program. It's still X. If we did not do anything to the program, X would still come from the left or right.
Right.
Yeah. So how does this help?
Oh yeah, how does this help?
Yeah.
We're going to talk a lot about that. We're going to spend the next hour or two talking about why this is so cool. Yeah, because at first you may say, so what I'm trying to convince you now is that it's easy to convert to and from. So it's not very onerous. And it doesn't hurt performance in terms of register allocation unless you do transformation. So let's take a look. So really the question is, where would this help? Why do you want to do this? Okay. Let's recall common set of structural elimination. So this was, we already did this. This is just a recall. The domain was basically variables to expressions, right? So we stored a quality of this. Basically what this said is that this was a available expression, saying that this variable expression E was stored in the value X, and we propagated this information. If you recall, this is what the flow function we came up with. And you'll notice, for example, that this is actually quite complex because you have to remove not only what X, so remember there was this complicated thing, you have to remove things where X was on the left-hand side, but also where X was on the right-hand side. Because if X appeared in an expression that we were propagating, then we actually have to kill that, and we also have to be careful with this X different from Y and X different from Z. So, do people remember the complexities of this example? You guys remember? Let's just and especially the two complexities are this, that we have to add these two constraints. Okay, otherwise we would have stored that basically like A is equal to A plus 1, which is totally wrong. And then we also have to be careful with this one. Make sure we actually remove everything where X occurs on the right-hand side of these arrows. Otherwise, we would basically be able to propagate one expression. Okay, does that make sense? You guys remember this? Okay, what does this look like with SSA? What does the flow function for this look like?
You get rid of the third one. Sorry, the special condition.
Okay, so we definitely can get rid of this.
And
Because, wait, hold on, because if there's no way, it means you can't have the same thing here, right? This will be,
if that's where you define it.
yeah, this is where you're defining it. There's no way, it will be a really weird, ill-formed program. It will basically, if this is X1, this is the only definition of X1.
You
So,
can also get rid of the X arrow star.
so we can get rid of which one?
X arrow star. Because,
Right, because there's only one definition.
and if you haven't, if you just defined it, nobody's read it yet, so you can get rid of that one.
So you can get rid of this one too.
Yeah.
Right, because this is the only definition, there was no other definition of the text. So basically, it turns out that a lot of these corner cases all have to do with variable redefinitions. And the fact that this could be the same as that, and all these kind of the fact that this variable x could possibly now, you're redefining x now, what is the implication of redefining x with respect to all the facts we had? So, whoa, look at this. This flow function now is just, you basically take in and you add x arrow y out z. Wow, what could be simpler than that? And that's really, what this really means is once you actually know that x maps to y out z, it'll map to y out z for the rest of the program, forever. Because this x will never be redefined, right? This will never be redefined. So and neither will these things. This y will never be redefined. This thing will never be redefined.
When we did that loop example, didn't we say something like,
Okay, so we have to be careful. Okay. So there is a little bit. What's loops? There is a little bit of. So we'll get to loops in a second. Yeah. Wait.
Well, it looks easier, but we're actually missing opportunities to do that.
Well, let's be careful. So you're right for a second. We have to make sure that we have to read. So okay, this part is easier. We have to adapt our merge. So we'll get to the merge in just 1 second. We have to be a little bit more covered with merge. Otherwise, we lose everything.
I'm not talking about merge. I'm saying that Y1 of Z1 in this case is probably never going to be used like, I mean, the chance is less because it's going to be Y2 or Z2. We have so many more variables that.
No. But the point is that if it's Y2, then it means that it's a different definition. The point is this. If it's Y2, it means that it's a different definition of Y, which means that if you look at your original CSV, you probably wouldn't have been able to use that because Y would have been redefined in the meantime. So it actually really isn't the same. It's syntactically the same, but the value will probably be different. So actually it's still okay. It's still okay, yes?
I just have small confusion. So here in this flow function you say in union with x, y on z.
Yeah.
But I thought for a single assignment, I don't see how the union works because I thought we only define it once. Can you maybe explain?
Yeah, so this assignment is the only definition of this x. This is the one and only definition forever of this x, and y and z are never going to be redefined afterwards because they were defined before once and that's it. And so I can basically add the fact that what this really tells me is that after this statement and forever after in execution, I will know that x will be equal to y off b.
Actually, why do we need the union? Why do we not just say x gets y off z?
Well, I mean, so so our facts are sets. So the facts themselves are sets of these things. So we're just doing we're returning the set in union with that. Right. Okay. Oh man, that sucks. Whoa. So I wanted to go through this, I guess, okay, let's go through this example. Let me do what I'll do here. So we jumped the gun a little bit, because I already showed you the SSA version. What I want to do is I want to just run CSV on this example normally without SSA, and then we'll do it with SSA, and we'll see kind of the differences. So, okay, so what's happening here? So if we run the normal CSV, the way we used to do it, this is I goes to A plus B, right? Mm-hmm. What about here? We get the same information as before. We also get X goes to I times 4. Yep. Now we go down this loop. What happens here? so we do this thing in here, so what do we get? We get whatever we had before, and we also get y goes to I times 4, right? Right? And now what happens here? Remember, this is the original version of CST, no SSA.
X and Y are balanced.
What happened?
X and Y are removed.
X and Y are removed, and I. In other words, total disaster. We lose everything. We just lost everything, right? Did everybody see? I mean, everything involves I. So we lost this, we lost that, we lost it all. So we just get the empty set. And once we get the empty set, so this empty set will percolate back here, which will make this the empty set everywhere. We'll get the empty set here. Okay, this is looking pretty bad, folks. And once you get the empty set in CSD and this kind of thing, so remember, so in this case, merge is intersection, right? We want things to be both on both sides, so empty set will really kill us. Okay, nonetheless, let's hope that maybe somehow it will be, but I doubt this will be disastrous, right? So what do we get here? Well, let's not record this information. We'll just get the same. We'll get the same I. But oh my gosh, here again we're going to get the empty set, right? Because this I is going to kill everything about I. This is not looking good.
We get to add I get C.
Yeah, but let's not. So let's. I'm only going to store information when the right-hand side is more complex than the left-hand side for CSV, because the kind of transformation I want to do is I want to transform an expression to something simpler.
Right.
So what is it? I mean, that's going to be for copy propagation. For CSV, what I really want to know is later on, if I see I times 4, I want to replace it with X. So I want this expression to be more complicated. Okay, this is total disaster, complete disaster, nothing works. Well, I'm going to guess this here that this is J times 4, but that's not going to help me in any way, right? And even if I did get it here, this is going to be intersected on this side, total disaster. Well, actually, maybe it's not a total disaster. Is this a total disaster? Maybe there's nothing, we're safe, but maybe there's nothing to optimize in this program. Is there something to optimize in this program? Sure, what is there to optimize?
A plus B.
What? Huh?
I just was assuming it's a good example, there will be something we can optimize.
Oh, but that's not, that is, your reasoning is completely flawed. Yeah, it's flawed, how dare you? No, actually, it's not flawed. It's accurate, but it's not the correct reasoning. So, okay, first of all, it's A plus B and not A plus B. Now, notice that we are sensitive. So far, we've kind of been very sensitive to the order of things, so that's a little bit sucky. So it would actually be nice to actually not be sensitive to the ordering of that this is B plus A versus A plus B. And there is a way to do that. You just canonicalize the expressions. You kind of order the variables in a particular way when things are associative. So there are actually ways of kind of storing the information. So we'll just assume that maybe this was A plus B instead of B plus A there. But if that were A plus B, we'd like to be able to, certainly this expression A plus B, we've already computed it. So why are we not able to do it? Because it's I. This darn wretched I is being killed here and here on both sides.
And the DS.
What?
The assignment in the left-hand side, the same as the X.
Oh boy. Oh, so that's, okay, this is
Can't
the
hear. What did he say?
thing. What?
What did he say?
He said, this assignment
Mm-hmm.
is computing the same thing as this assignment.
Post-copy.
Post-copy propagation. So semantically, so every time you compute this value, it'll be exactly the same value as the one in X. The reason why we're not seeing it is because we haven't done copy propagation. You're absolutely right. So this shows an example where actually doing copy propagation before CST is a good thing. So you want to do copy propagation, so this I goes to this J, and this I goes here. But actually, no, you can't.
Yes.
Wait a minute. You can't do that. What?
I mean, the I is changing.
Yeah, the I's changing, so how can you copy propagate it?
You reorder. If you have
Oh, you reorder it. Come on, okay, so now you want to reorder things. It's getting very complicated.
perfectly fine.
I have a better solution. We'll talk about it. We'll see. This actually is going to solve all these problems. Right? I mean, we're not. This thing is going to make all of this just works like a charm. No need to like, so does everybody see? If we could start out copy propagate this I here, but this is not, but we can't because this
You will be able to.
assignment is killing, is kind of causing us trouble. Now, okay, so the moral of the story is we're not going to finish the example right now. But we will finish it on, wait, on Thursday, no, today is Thursday. Tuesday. Okay. All right, see you guys next week.